Log on, tune in, find out. Another good idea from Cambridge.
I'd like to introduce Mike Campbell, who's Professor of Medical Statistics at Sheffield. And as you're going to hear, Mike has worked in this area for a long while with lots of examples of interesting questions and pitfalls of these trials. So, Mike, over to you.
Thank you, Sarah. Okay, good afternoon everybody. Can everybody hear me? Yep. Thanks very much, Sandra, for inviting me to this symposium. I feel very privileged to be here. I'm particularly interested because design to me is a really important job for a statistician. You can always reanalyze an experiment, but you can't redesign it and run it again. So I always think that it's very important to have the design right in the first place. I apologise for lack of an abstract in the proceedings. I have no idea why that happened.
There is one on the website.
Okay, so this is a bit like a football match really. It's a game of two halves. The first half I'll talk about the design of a study to reduce recruitment bias, and unfortunately to Alan I'm not actually talking about analysis of this particular trial because it's actually just about to run. And then when I was invited to do this talk, I thought it was an opportunity to look at some of the ad hoc procedures I tend to adopt for doing sample size calculations, and I thought I'd just test out some of these using simulation to see how effective they were, and so I'll just report some of those results. So this is, I'll start by talking about recruitment bias, which Alan has very kindly primed you all to expect to hear, and I'll talk about this particular trial which some people are very familiar with already since the originator is in Cambridge. It's a diabetes care from diagnosis. And the idea there was to train general practitioners in a rather newfangled American idea, which was called patient-centered care for people with type 2 diabetes. And so the idea there was that diabetes is a chronic condition that people live with, and often they're better experts about the disease than the physicians who are treating them. And therefore, why not give them responsibility for looking after themselves? Unfortunately, British general practitioners tend to be much more patrician, and they prefer to think they're the experts and they tell people what to do. So we had 41 practices were agreed to consent. I think we started out with 60, but 19 of them wouldn't take part. And in the end, we ended up with 250 individuals out of 360 who were newly diagnosed. And this is the important thing, that they were newly diagnosed with type 2 diabetes, and they were completed follow-up after 1 year. And the intervention was that the general practitioners got a day and a half's training in this newfangled American technique, looking for why patient-centered care should work and how you might impart it into their patients, and in particular to encourage the patients to ask questions, which was inimical to the GPs in that era. The main outcome variables were things like HbA1c, which is a measure of glycemic control in diabetes. The important point here is you can't blind the study. You're either going into, when you arrive, and this is again where we talk about the ethics, usually people in Britain in particular stay with one particular practice, so they're actually they're going to be an intervention, or they're going to be doing patient-centered care or not. And at the time we didn't actually think about putting a little sign up saying your GP has recently been trained in patient-centered care. If you don't want to, you can go to another practice. But that's something which we learned, because it was a long time ago. I was only 12 at the time, as Don Berry said when I did this trial. So here's the outcome. It was actually ended up 142 patients in the intervention group and 108 in the control. And this came as a bit of a surprise to me at the time, because I thought that type 2 diabetes was something which was completely objective really, but in fact it's not. A patient comes into the practice, they're overweight, they're a bit sweaty, they're getting a bit thirsty. The GP has just been trained in looking at for people with diabetes. They test them, and in fact I think there's an estimate that 50% of the people with type 2 diabetes in the population have not been diagnosed yet. And so in fact they were just diagnosing more patients. So then we have this rather worrying thing: are we actually looking like for like? Are these patients in the intervention group the same as the patients in the control group? So that was a problem really. Well, further down the line, 10 years later, I designed another study. This is called Desmond, and in fact it's quite interesting because it's diabetes education and self-management for ongoing and newly diagnosed diabetes. Now this is actually the brother of another intervention called Daphne, which is diabetes dose adjustment for normal eating, which is for type 1 diabetes. And the idea here was that you train people in diabetes to look after themselves properly, and in particular to try and give up smoking and to lose weight. Now, I mean, I actually designed this trial, and I knew about the problems of recruitment. In fact, the paper by David Torgerson that Alan referred to castigated our diabetes care and diagnosis trial because, in fact, it had selective recruitment. In fact, I'd pointed that out in the actual paper itself, but David didn't care to mention that, but never mind. Anyway, this is type 2 diabetes. But the point here, this is also a cluster randomized trial because Daphne and Desmond are given in groups, and Alan kindly mentioned that in fact you get this synergy, that educating people in groups is actually often much more effective than educating them individually, and that they teach each other as much as they learn from the instructor. So we ended up with, it was quite a large study. I did the sample size and actually slightly got some of the numbers slightly wrong, so it was bigger than I expected. 207 practices, 824 patients. I say the treatment was practice-based, so the courses were given through the general practice, so they were again clustered, and the main outcome again was HbA1c and some other scores as well. Well, you'd have thought we'd have learnt, but we ended up with 437 patients in the intervention group and 387 in the control, which is a bit, I thought, oh dear, I mean, here we go again. What I did in the analysis was I actually then matched the people in the intervention group with people in the control group who had similar severity of disease, particularly HbA1c, and reanalyzed them to try and see whether there was actually a serious bias going on. And in fact, this Desmond trial was a complete failure in that we totally failed to change their HbA1c compared to the control group. And in fact, adjusting for baseline covariates made no difference at all either. It still remained a complete failure. The only interesting actually, which was the authors picked up, was that in fact there was an improvement in the smoking rates in the treatment group. But when I reanalyzed the data, I discovered that some of the control group appeared to have taken up smoking during the period of the trial, which was rather worrying as well. But anyway, so we come to the third trial, my third attempt at designing a trial in diabetes. And this is called REPOSE. In fact, one of the first rules of designing studies in Britain is you must have a good acronym, and this stands for Relative Effectiveness of Pumps over MDI in Structured Education. In MDI are multiple dose injectors, which are for people with type 1 diabetes now. So this type 1 diabetes is where they're totally dependent on insulin. Now, insulin pumps sound really good and really technological, but in fact they're not that sophisticated. All they do is you press a button to give you an injection of insulin rather than having to use a multiple dose injection, so you don't actually have to inject yourself, but there's no sort of feedback loop or whatever, so they can't actually automatically control your level of insulin. But they are perceived to be quite desirable, so there's a problem about whether people would want to come onto this study purely so they might be able to get a pump. So I did the sample size calculation, and one of the interesting things is these pumps are really expensive, and so we were restricted partly into how big the trial could be. So that was one of the things I was trying to, when I did the sample size, was to try and minimize the number of patients according to how many pumps we actually had. So we had each centre, we got 7 centres were willing to take part, and we could deliver about 6 courses in each of the 7 centres. And you, again, with the Daphne and the Desmond programme, you train people in groups of about 6 to 8, and though so it's a clustered randomised trial. So the principle really was, we decided now that we're going to recruit and consent patients before randomisation. So we took a fact that we can randomise clusters to treatment. So in fact what we did was we recruited patients and said you're going to be given the option of either having a pump or an MDI, and then you're given choice of 2 dates for which course where they wanted to be given the courses. So the courses are usually given over an entire week. And I said the courses work best when there's synergy between the patients, so you need at least 6 people and not more than 8. When you've recruited both dates with 8 subjects each, then we randomise the dates to either the pump or the MDI, and we then told the patients that they were going to get the pump or the MDI. So that was, they'd already consented to be in the trial at that particular time. So one of the problems really is what happens if they consent and then withdraw, but before we've actually just randomised them, because it takes a little while to recruit these people into the different dates. So then we just substituted another patient into the particular one. What happens if they withdraw after randomisation, but before the treatment starts? So here we had a reserve list of people who are willing to come on at least one of these dates, and we chose the first person on the reserve list in that date. Some people said we should actually randomise to choose who should come on. We decided if we had a strict list, which was kept by somebody independent of the trial, that would be all right. And if the person refused, then we'd choose the next person on that list. So they'd have to then get whatever was allocated that particular date. They didn't have any choice. They said, you're going to get the NDI or the pump. The investigators will also try and like to balance baselines, in particular the HbA1c at baseline, because this is going to be the outcome as well. And so what we tried to do there was, if patients could come on either date, we used a sort of minimization algorithm to allocate the patients to the date. So that was for the first 4 courses. So that means we'd have 2 in the intervention group then and 2 in the control group. Then after the 4th course, we're going to use a minimization algorithm again to decide the allocation of the 5th and 6th courses, rather than simply tossing a coin or randomizing them to one or the other. So the conclusion of this particular half of the talk really is that, say, cluster trials are in general not blind, so they do suffer, or they can suffer from recruitment bias, and in fact it's really quite difficult to try and get around this recruitment bias in many ways, particularly when the clinician doing the recruitment is the same as the one giving the intervention, or if there's some incentive for people to go on one treatment rather than the other, such as, for example, wanting a pump. And I said Repose is an attempt to minimize these biases, but it is a somewhat complicated design which we have to keep an eye on. So I just thought that would be the first half of the talk. How are we doing for time? Right. So the second half would be just well, these trials, I've been using various sample size formula. Alan has talked about the design effect. I'm not a great fan of sample size calculations. When you're reviewing protocols, you do see sample size calculations, but there's a wonderful quote about a sample size calculation is simply a guess masquerading as mathematics. And there's a lot of post hoc justification goes on about sample size calculations. I would say that my own belief is actually I think they're important in a protocol, but not principally to say, well, what's the power of the study, but because you nail on the mast what you think is a clinically important effect. You actually say before you design the study, well, we think this is a clinically important effect. So when the study comes out negative, as Alan said many cluster randomized trials do, then the clinicians can't say, well, actually, we think these treatments are equivalent, because you can point out that the confidence interval they estimate will include something that they previously had described as a clinically important effect. So I think that's one of the important things, that it does actually say what the outcome is going to be and what the effective size is. In fact, various reviews of design of trials have discovered that it's amazing how often trials are written up, and in fact the primary endpoint is suddenly mutated into something different to what it was in the protocol. It's an interesting problem. But anyway, these are some of the issues about sample size formula. So Alan's already talked about some of the issues, but the simple fact really is that if you've got N is the sample size for an individually randomized trial for a particular effect size, power and significance level, and that NC is the sample size for a cluster design, then you simply have the number in the cluster is N times the design effect. And in the sorts of designs that we're putting in, you have the design effect, as Alan has also pointed out, is 1 plus n prime minus 1, where n prime is some sort of average cluster size. And Sandra's going to be talking about variable cluster sizes, so from now on I'll talk about fixed ones, times the ICC. Now, the ICC is defined in this particular case as the variance between the clusters divided by the total variance in the groups. So in this particular case, the ICC has to be positive. So in other words, the design effect is always going to be greater than 1, so you always have to inflate the sample size to allow for a clustering design. But there are situations, I think, where you can actually have negative ICCs, and in those are the situations in like health economics, where you've got a fixed amount of money you can give to a particular resource, and if you give it to one set of people, you're not going to give it to the other, and you can actually end up with negative ICCs. But I'm not going to be talking about that. So given a fixed number of clusters, then we need to fill up, for example, in the Daphne study, we needed to fill up our courses. They weren't going to run courses which were less than 6 people. So calculate the sample size n, and then, well, that should be NC really, the clustered one. Then divide that by the number of people per cluster. And then you need to round that up in order to get a whole number of people in each cluster. And then the total sample size adjusted is just the 2 times the k times m. So luckily also, Alan being the guru of sample sizes, defined the notation. So we all use k for the clusters and m for the number of patients per cluster. So the question is, do these sample sizes work very well? Well, there's 2 things about sample size estimation. One is that we think we have m at the analysis stage. So we need to know m at the analysis stage, not at the design stage. So when you have dropouts, they will reduce the number of people per cluster. So in the Daphne study, we'd have people dropping out. So we wouldn't have 8 necessarily in the cluster, but perhaps only 6. So that will actually reduce the design effect, because remember it's 1 plus m minus 1 times the ICC. So the design effect goes down. Therefore, the required number of patients would go down as well. Therefore, we might actually get an improved power from that particular design. But of course, we've got fewer patients, so we need to balance the 2 out. And the other question is, we often use baseline covariates. And in the Daphne study, or the Desmond study, we looked at the HbA1c at baseline, and we used that to adjust the outcome. And the point here is that since it's using the same variable at baseline as you're doing at the outcome, then you should be able to reduce the variance of the outcome variable conditional on the baseline. And how does that affect the ICC and the power? So the analysis, I used what's called generalized estimating equations in R. It uses a working correlation to allow for correlations within the clusters. And we use what's called an exchangeable correlation structure. So basically, that says that patients within a particular cluster, it doesn't matter what order they're in. So it's not like it's sort of like a time series, because the other use of GE is in longitudinal data, where in fact you can't randomize Mondays to be before or after Sundays. So it's conventional in GE to actually require 40 clusters in total to use it. And for this particular talk, and because I didn't have much time, I'll restrict to Gaussian outcomes. So the problem with GE is, I said, it's not very good for small samples. There's various corrections that have been proposed throughout the time. The ones that I think are particularly effective are these ones by Mankel and it's actually de Rouen in 2001. And what they said was, well, the GE tends to underestimate the sample size, so we need to calculate what's called a robust standard error, and then we adjust that by multiplying by square root of 2k over 2k minus 1, where k is the number of clusters. So you inflate the robust standard error just slightly, and then instead of using the p-value from the z statistic using a normal distribution, we'll use a t distribution with 2k minus p degrees of freedom. In R, the GE doesn't routinely give Mankel's corrections, so I had to reprogram it to do it for me. A simulation exercise, I used 3 effect sizes, 1, 3 and 5. S squared B is 1, S squared W is 19, to give an ICC of about 0.05, which, as Alan kindly pointed out, is quite common in these sorts of primary care trials. This gave standardized effects of about 0.2, 0.45 and 0.67, which in the old Cohen's sort of sizes are small, medium and relatively large. And I just stuck to a 2-sided 5% significance and 80% power. So the model that we generated was a very simple one with a random effect and an effect due to treatment. And there's the various notation for that particular trial. We did, to find the power, I did 5,000 simulations. It was interesting to hear Andy Grieve this morning talking about 1 million simulations. I worked out 5,000, gave me about a standard error of 0.03 for estimating power or significance, and I thought that would, 0.003, so I thought that would be roughly reasonable to have that. So you just simply simulate the model 5,000 times and find the proportion of times we got a statistically significant result. And then for the type 1 error, we simply remove the design effect, so remove the effect of the treatment and simulate the model again 5,000 times and find the proportion of times that p was less than 0.05. And the way I'm thinking about it, when you're planning a trial, you don't know whether the treatment effect is there. You calculate the sample size. So it's very difficult to interpret a power unless your type 1 error is actually 5%. And therefore I thought it was important to check out whether this particular procedure gave us a valid type 1 error before we could interpret the power. You can't actually fix the type 1 error at 5% to determine the power. So here's the simple calculation for a simulation where there's the design effects. These are the sample sizes required by a very simple sample size formula. These are the number of clusters, which are relatively large for sort of practicalities. This is the type 1 error as produced by the usual R. This is the average type 1 error produced by R. And you can see that actually the type 1 error is slightly large, but when you put in Mankell's corrections, you get a reasonable sample type 1 error for these particular studies. When you look at the power, this is the ordinary power unadjusted for Mankell. You can see that it appears to overestimate the power, but when we use Mankell's corrections, the power is actually reasonably okay. And here's the working this is for a sample size of, cluster size of 2, I should have mentioned. So a relatively small cluster, so large numbers of clusters. And you can see the working correlation appears to go, this is the average working correlation, goes down as the sample size goes down. So if we go on to 20 patients per cluster, then we have, we end up with the smallest number of clusters is 8, which is 4 in the treatment arm and 4 in the control arm, which is supposed to be much too small to be using GE, but actually Mankell's type 1 error does pretty well. And you can see the power when we corrected using Mankell's corrections, the power is actually reasonably good. It just underestimates the power somewhat when we go down as little as 4 clusters per group. So in fact, I was reasonably reassured that these things were actually working fairly well. So then I thought I'd look at the problem about looking for missing values. So the conventional way of approaching missing values is to say, well, we think about a certain percentage are going to be missing. So we simply divide the total that we'd think we're going to get by 1 minus the proportion of missing. So if we thought that 20% were going to be missing, we divide by 0.8 to inflate the sample size to allow for the increased number of missing values. So what I was saying before was that, of course, we're going to get fewer numbers in the clusters than we might have, but on the other hand, the number of clusters, the number of, because I'm assuming that the people are going to be missing at random, now instead of having a fixed cluster size, the cluster size is actually going to vary. So what I did, to go into missing values, I just assumed we got a 20% missing dropout rate, and I assumed that they were totally at random, so I just used a uniform distribution to decide which ones were missing, which ones weren't. I used the ordinary sample size calculation to calculate n, and then I inflated it by this 20% to actually get a sample size which would I then use in the simulation. So here are the results, and you can see this is the unadjusted ones that we had before when we did the simulations. This is now the adjusted sample size when we account for missing values. This is again for a small number of clusters too, and you can see now that we've increased the number of patients per cluster to allow for the missing values, so that when we do the analysis we'll end up with approximately the unadjusted sample size here. Here's the adjusted number of clusters, so we actually increase the number of clusters slightly to allow for the fact that we're rounding these things up. And you can see here that the type 1 error is actually quite well preserved, and in fact the power is quite well preserved as well. So this adjustment factor, this very ad hoc adjustment factor seems to work quite well. When we allow for 20 patients per cluster here, then again we've got, these are the usual sample size calculations that we got. This is when we adjust it to increase the number of clusters and number of patients per cluster. So now we end up with 10 clusters rather than 8 to allow for the missing values. And in fact the type 1 error goes a little bit awry by the time we get down to 4 clusters per arm or 8 clusters. It's just slightly larger than it should be, and the power appears to be rather overestimated. We've got slightly greater power than we might expect. In other words, we appear to have recruited perhaps rather too many subjects when we adjust by this simple ad hoc factor, so we end up with a slightly greater power than we thought we would have had. So the other thing I want to do is look at adjusting for covariates. So in here you've got a model where we simply add a factor with a baseline covariate, and the point about it really is if you're actually adjusting for something like HbA1c, you've got the HbA1c at the outcome and you've got the HbA1c at baseline. What's causing these variables to cluster? Now it could be that in fact the sort of things that cause it to cluster at the outcome are the same sort of things that cause it to cluster at the beginning. So with general practice, you have patients of a certain type, they're in a certain area, and so it could be that the random effect is the same in the baseline covariate as it is in the outcome. So this is just one particular scenario, and it's possible that actually the random error is also similar in the two groups, although those will be totally independent random errors. So we assume that they have the same basic distribution, just different, they're both independent. And so I just used beta equals 0.05 to see what would happen. So when I ran the revised sample size calculation, well, the simple ad hoc method there is that you reduce the sample size by 1 minus r squared, where r is the correlation coefficient. And this is based on the fact that the variance of y given x is the variance of y minus beta squared times the variance of x, which is just the variance of y times 1 minus r squared. So the conditional variance of y given x is actually reduced by a factor 1 minus r squared. However, if we actually looked under model 3, which is the model I gave, you find that the variance of y is actually greater than the variance of x, is given by this function here. The variance of x is simply sigma squared w plus sigma squared b, which is actually less than the variance of y if beta is greater than 0. And the variance of x given x is just sigma squared w, the residual variance. So if we actually used the variance of y given x, which is the one I'd say is the ad hoc thing you might use in a sample size calculation, and in fact the variance of y is equal to this particular, just the residual variance, then this thing, what you would want is that this factor here is going to be less than the actual true residual variance. And this occurs when r squared is greater than the intra-class correlation. So what that means is that we're going to plan a study which is actually going to be too small if r squared is greater than the ICC. So I thought, well, I'll just do some simulations to see whether that's true or not. And in the simulations, I put r squared about 0.25, the ICC is about 0.05, so you can see that r squared is actually a fair bit bigger than the intra-class correlation. The sample size was based on a variance of sigma squared w plus sigma squared b equals about 20, r is about 0.05, so we'd have expected the variance to be about 15 in the adjusted formula. However, in fact, the conditional variance is in fact about 19. So when we did the sample size calculations, this is again for 2 patients per cluster, I found that the power is considerably reduced, and it's not 80% at all. The adjusted correlation, the working correlation used in the model is actually reduced a fair bit, especially when the numbers of clusters are relatively small. And so what that's saying is that the ICC is actually reduced as well, because we've got a factor at the baseline which has also got the same sort of correlation structure. So when we allow for it, we reduce the ICC, reduce the adjusted working correlation. And the simulation more or less got the right sort of correlation structure that I'd expected. It's just slightly underestimated from what it might be. And when we have m equals 20, we find, in fact, the things are just as bad really. This is m equals 20. We've only got 6 clusters now, 3 per arm, which is stretching it a bit for GE. We found that the type 1 error is increased, and the power is not really up to 80% at all. So I'm saying that this simple procedure, an ad hoc procedure to adjust the sample size for the correlation at baseline, is not really a necessarily good thing to do in cluster randomized trials. So the conclusions I come to is that the GE performs well with continuous data and only slightly underestimates the power when the number of clusters is even down to 8 or 4 per arm using these small sample corrections. When the corrections for missing values performs reasonably well, perhaps because although the design effect is smaller, leading to greater power, so the cluster size is varying, which will reduce the power. The larger clusters overestimates the sample size, and so it could be that actually we're being slightly too pessimistic when we're trying to adjust for, it's possibly because with large clusters, individual people within a cluster missing is actually less important. And in particular, I haven't talked about possibility of imputations. You could perhaps impute the missing values. If you knew what the cluster variable was, you'd have quite a good chance of imputing the cluster variables. The simple adjustment for a covariate results in a lower than expected power because adding a covariate didn't reduce the variance as much as it might have been expected. However, this does depend on the expected relationship between y and x. So you could actually have other models with related y and x, which would be different from this, which would give different results. I haven't had time to go through all different sorts of models yet. Okay, thank you very much.
Questions, comments for Mike?
Can I ask you about the when you use the minimization?
Yeah,
So you were using the Pocock-Simon
yeah,
type of
yeah.
minimization, and it wasn't clear to me what you were actually doing. That you were using a difference metric based on the numbers of subjects in the cluster.
Yeah.
Thus far, and did it work?
Well, we haven't. The study is about to start.
Oh, I see.
So any comments would be gratefully received, because we're just writing the statistical analysis plan even as we speak. I mean, basically, it would be, I think the critical thing is whether you've got an HbA1c greater than 7.5%. And so what we do is we'd say, well, if you randomise them to one cluster to A and one to B, what would the imbalance of people over 7.5% be? And then we'd look at the alternative imbalance if they were over less than or greater than 7.5%, and then we'd choose the design which minimised the imbalance between the two. That's the way we do it.
And you're just going to use a bias clone of 2/3 or something like that?
And no, I think it would just be deterministic then.
That would be deterministic.
Yeah. It was only between the two, so yeah. So yeah.
How do you realistically expect to have the same number of patients as a cluster? And again, same question, do you consider randomness in some number of patients in clusters?
Well, the way that the Repose trial is being designed, we'll try and keep as many patients to the cluster. I think actually the dropout rate in Repose is going to be relatively few, because there's quite a strong incentive for the patients to be in the trial so they can keep hold of the pump. So I don't think there will be too much dropouts in this particular trial. But, yeah.
Mike, was there not another small sample correction proposed? I think by Pan and Wall.
Pan and Wall, yes, there was. That's right.
Distribution.
Yep, that's right.
Did you look at that at all, or?
I did, but it didn't. I mean, and in fact, there's two papers in Statistics and Medicine this year which combine them both. They combine Mankell's, de Rohan's, and Pan and Wall's. One's by Mike Kenwood, and then the other one's by somebody in America. The Pan and Wall one is quite interesting, because what that does is, because you've got a robust standard error, but if you assume that the ICC is the same in each of the clusters, then you can take an averaged ICC as well and use that instead. But in fact, the simulations I've seen say that the Mankell one, which is basically to do with the bias of small samples, works reasonably well, and I haven't actually got around to doing the other one, which would be...
Just a second quick question. Adjusting for covariates, do your results apply to both cluster level covariates and individual level covariates, or just individual level covariates?
These are just individual level covariates, yeah, that's right. Yeah.
So adjusting for cluster level covariates should also give you more precision.
It should do, yeah.
Just going back to the first half of your talk about
Yeah.
recruitment bias, I mean, the fact that the recruitment bias is a really serious threat to the validity of cluster trials.
It is, yeah.
And even your attempts to pre-specify which patients were going to be in the trial before you actually randomise the clusters, are valid, but obviously can't get around some of the problems you then talked about later. I've come to the sort of conclusion that when you're faced with a recruitment bias issue, that cluster trials are actually really not a sensible option.
Yeah.
The recruitment bias is a very serious bias. There are other examples which you know well about, published by Amanda Farron and others.
Yeah.
It shows that the unknown, unobserved covariates can have such, which have determined patient eligibility, can be so serious that actually completely violates the intended randomisation. And I really think we should have, maybe you should be saying when the recruitment bias is an issue, cluster trials is really not an option.
Yes, I tend to agree. I mean, I was involved in a few trials where they could have done cluster randomisation, but they didn't, for reasons partly to do with that. One of the problems with individual randomised trials in that case is things like ensuring compliance, whether they've actually done the thing. And the problem with contamination, again, is another major problem. So it's just a big issue, really, in how to evaluate these interventions. Yeah.
Can I ask a second completely unrelated question? When you had your model where you were adjusting for the baseline covariates in the second part of it, you said, let's imagine they had the same random effect.
Yeah.
Would not a more realistic model be that they would partially share the same random effect, and so you'd actually have you'd have correlated random effect rather than the same random effect? Would that be a more realistic model, do you think, for covariate adjustment?
Yes, well, I mean, that's another alternative, yeah. I think I was thinking of it, if you've got baseline HbA1c and you've got outcome HbA1c, then why are they, well, they're clustering partly because they're all in the same course, so the effect...
And they're also clustering because then the synergy, when they take up the intervention, that's going to be clustering which is introduced through the intervention, which won't be there at the baseline.
And it won't be in the control group either.
Well, and that would also make a difference whether you want to assume the same clustering in the
Correct,
control and the intervention.
yes, there are lots of ramifications on that, yeah.
I would have thought in that last case that what you need is the conditional variance, which I guess you are interested in using, but also the conditional ICC.
Yeah.
And that must be a quantity that can be estimated.
Yeah.
I mean, you know, there's within correlation, there's between correlation.
Yeah.
But surely that's the quantity you want, and I don't think it just depends on the cross-sectional ICC and the correlation. I think it depends on something else as well.
Yeah. I mean, well, you can see the working correlation in the model was less when I put the variance in, but that was one particular model, yeah, but you're right, Okay.
We do have time for another couple of quick questions if there are any. Okay.
No, good.
Thank you again, Mike.